In this video, we're going to talk about finding the surface area of a solid of a revolution. So, let's suppose that we're going to find the area of the surface that we're going to generate by revolving the graph of a function on an interval from a to b about the x-axis. Okay. And just like what we did for arc length, we're going to assume that we have a nice, smooth function over the interval from a to b. Meaning, again, that the graph has no sharp corners, has no cusps, it's connected everywhere. We don't have any issues as far as that goes. Just like what we talked about every other time we've been doing an application of integration, we're going to divide up our interval into pieces. So we're going to partition our interval from a to b into n subintervals. And we're going to use some geometric object that we can find the quantity that we're interested in easily, add those things up, and recognize that we have a Riemann sum, and then take a limit that gives us a definite integral. In this case, we're going to use what I'm going to refer to as bands. We're going to approximate surface area using bands. So let me show you what I mean. So we've got some function on the interval from a to b. We've taken the graph of the function and we've rotated it around the x-axis. So if we thought about having the area underneath that curve, we would get a volume, like we did back a couple of chapters ago. We would get a volume. Here we're just interested in the surface, however, just the outer layer. Okay? So what I mean by approximating using a band is think about if we had that line segment across the curve on the interval from on the ith subinterval. When I rotate that line segment, I get this band. I get what's referred to as a frustum of a cone. So this piece here would give you what's referred to as the lateral surface area of the frustum. Okay. And it's true in general that the area of the frustum, that last lateral surface area of the frustum, is 2 pi RL. R is the average radius of the frustum. So notice that there's two radii here, right? There's this one on kind of this bigger circle, at least in my picture, this one on a bigger circle, this one on a smaller circle. So we have two radii. The R here is representing the average of those two. So as far as the frustum goes, it would be the radius that would be right in the middle. That would be your average radius. L is referred to as the slant height. That's the length of this diagonal segment on my picture, which would be, of course, be the same as this length here. All right. So we're not given R and L in general. We're given a function that we've rotated. So we need to get R and L in terms of the function that we're given. All right, so let's think about the radius first. For the radius again, the radii would be this big radius here would be your f of x sub I minus 1. The smaller one here would be your f of x sub I. Again, which one's bigger and which one's smaller doesn't matter because we want the average of those two things. Now, in general, it's true that when you take the average of two numbers, that number is in between the two numbers. The average is in between the two numbers that you started with. So the average of f of x sub I minus 1 and f of x sub I is going to be in between those two function values. Now remember, we said we were going to have a nice, smooth function to start with. No holes, no sharp corners, no cusp, none of that stuff, right? Well, the no holes idea means that the function is continuous. So your average of the function values is an intermediate value of the values of the endpoints. So we can use the intermediate value theorem to guarantee that we have some sample point in the ith subinterval that gives us a function value equal to the average of those two function values of the endpoints. Okay, so f of x sub I star will be equal to the average of the two function values at the endpoints. So that means that what we have is we have the r in terms of the function, which is one of the goals that we were going for. All right, now we need the L in terms of the function. The L, again, was the length of this line segment. Well, notice we already have a way to approximate that in terms of the function from the stuff that we did for arc length, right? We use the mean value theorem to give us a sample point that would give us the length of that line segment in terms of the derivative of the function and delta x. So when we do the mean value theorem, we know that we get something that gives us the length as the square root of 1 plus derivative squared times delta x. Now in this particular case, though, the point that we use to get the derivative to work doesn't have to be the same as the point that we use to get the function to work. That's why I've got a double star rather than just a single star. Alright, so when we put those two things together, we get an approximation to the surface area is going to be the summation of 2 pi times the function times square root of 1 plus derivative squared times delta x. Now again, this is really close to a Riemann sum, but it's not quite a Riemann sum because remember it's not the function of the same sample point. We have two different sample points. Now, of course, what are we going to do with all of these intervals? We're going to get them smaller and smaller and smaller. You take n goes to infinity. So even though this is not quite a Riemann sum, when you take the limit, you could really show that this is the limit of that summation on the previous slide does turn out to be a definite integral. And if you think about it, it makes sense because the length of the subintervals gets smaller and smaller and smaller, which means your x by a star and your x by double star have to approach each other. So we can get our formula for the area of the surface generated by taking the graph of f of x and rotating around the x-axis is going to give you the integral from a to b of 2 pi f of x square root of 1 plus the derivative squared dx. All right, let's do an example and verify that the answer we get actually makes sense. Let's say we graph the surface, we graph the function y equals x and rotate that graph about the x-axis, where the interval that we're interested in is from 0 to 2. Well, just using our formula here, well, certainly the derivative of f of x is 1, so we'll get integral from 0 to 2 of 2 pi f of x is x, f prime of x is 1, so we get square root of 1 plus 1 squared. So this is just square root of 2. So the pi and the square root of 2 can come out in front, and then you anti-differentiate 2x, you get x squared, evaluate from 0 to 2, and that gives you 4 pi root 2 for your answer. Now let's see if we can verify that 4 pi root 2 really makes sense in this context. When we take the y equals x and rotate it about the x-axis, we get a cone, an honest-to-goodness cone. What we're interested for this cone is this lateral surface area, the stuff on the sides, not the circle here at the bottom. We're just interested in the sides because we're rotating the graph, not the entire region. All right. So this would be the lateral surface area of a cone, and the formula, if you remember, for the lateral surface area of a cone is pi r L. R is the radius, L is the slant height. Well, the radius is 2, and your slant height is this length here, this diagonal. Well, if this length is 2 and this length is 2 this way, we get a 45, 45, 90 triangle, which makes the slant height 2 times the square root of 2. So pi times r times L is pi times 2 root 2, which gives you 4 pi root 2. So we really do get the same answer in this particular case. Let's do another, before we do another example, let's talk about how we can write these formulas in general, both arc length and surface area. Because there's a lot of things to remember. Am I rotating around the x-axis? Am I rotating around the y-axis? Am I just looking for arc length? Am I looking for surface area? So let's see if we can make the formulas a little bit more general and talk about it in a general sense. All right. So this blue curve is just some arbitrary function. These dx, dy, and ds are representing differentials. So your dx is your change in x, and your dy here is your change in y. Your ds then is the change in the arc length. Now again, it's not the exact length of the change in the arc length, because it's not the stick, the line segment isn't quite the curve that might be bent. But as your delta x gets smaller and smaller, your dx gets smaller and smaller, your ds really will be really close to what the change in the arc length is. Notice that we've got a right triangle relationship here. So we actually use that relationship to help us get concise formulas for the arc length and the surface area. And it doesn't matter whether or not the integral is in terms of, the function is in terms of x or in terms of y. Okay? So looking at your first one, let's say we had the arc length. Well, remember your arc length is either square root of 1 plus f prime of x dx, or f prime of x squared dx, or the square root of 1 plus f prime of y squared dy. Notice that you can get those formulas by dividing this equation either by dx squared or dy squared. If you divide by dx squared, you get 1 plus dy dx squared, or 1 plus f prime of x squared. Okay? If you divide by dy squared, you'll get 1 here plus dx dy, or f prime of y squared. And then, pardon me, you get, if you have ds squared, you get to take the square root to get the ds by itself rather than having a ds squared. And then you would also multiply by either the dx or the dy to get your appropriate differential. So you can remember your arc length formula is just the integral of ds. What about your surface area formula around the x-axis? Well, we had f of x when we did the development before, but f of x can be thought of as y, and then we had square root of 1 plus f prime of x quantity squared. That's our ds again. So when we have the surface area revolving around the x-axis, we can just think of this as 2 pi integral of y ds. The y is giving you the radius, the ds is giving you the arc length. If you're given a function of x, you're going to replace both pieces with the appropriate function of x's. If you're given a function of y, however, you don't need to replace the y. You only need to replace the ds. Similarly, when we have the surface area for revolving around the y-axis, your radius then becomes x rather than y, but your ds is the same. It's still a change in arc length. So again, these are concise formulas for remembering surface area. So let's do an example here. Area of the surface generated by revolving x equals y squared about on the interval from 0 to 2 about the x-axis. All right. We are given x as a function of y. It will probably be much easier for us to, if we're given a function of y, it's probably much easier for us to deal with everything in terms of y's, rather than having to solve for y in terms of x first before we go on to anything else. Because if we did that, not only would we have to change the function, we'd have to change the interval. Okay. So it's much, much easier to leave this in terms of y and deal with functions of y's than it is to try to convert everything to functions of x. All right, so function of y, take the derivative, we get 2y. According to the formulas that we talked about on the previous slide, when you rotate about the x-axis, your integral is y ds, because again, the y is the radius. When you rotate about the x-axis, your radius is the y coordinate. All right, so we're given function of y. We want everything in terms of y. So I do not need to substitute anything for that y right there. It's already in terms of y. Don't put it in terms, try to put it in terms of x. It's already in terms of y, and we're doing everything in terms of y. For your ds piece, you're going to do square root of 1 plus derivative squared. The derivative was 2y, so we get 4y squared as the other piece. This integral now you can do is u substitution. When you let u equal what's under the radical, your du would be 8y dy, so you have to divide by 8, and then you've got a 2/3 that'll get come out when you do your antiderivative. So that's where the 1/6 essentially comes from. So you get pi over 6 times that expression to the 3 halves, and then you plug in your values, and you'll get 17 root 17 minus 1 times pi over 6.